A galaxy is dying. Right now, a billion years after the Big Bang, a group of colliding galaxies is losing its own air, blasted away by winds moving hundreds of miles per second. James Webb caught it happening. The gas plume stretches 7,000 light-years. Scientists say the galaxy could be dead in 50 million years. We'll follow the collision that started it, the supernova storms that drive it, and what it might mean for our own Milky Way. If you enjoy the ride, like and subscribe, it means everything. Now, brace. A galaxy is alive when it makes stars. That sounds simple, but it changes everything. Think of a galaxy like a city. A living city has construction everywhere, new buildings going up, cranes moving, energy pouring in from every direction. A dead city has empty lots, old structures slowly cooling, no new growth. In a galaxy, stars are the buildings, gas and dust are the bricks. As long as a galaxy has gas, it keeps building. The moment that gas runs out or gets ripped away, construction stops. Forever. For a long time, scientists had a clear picture of when galaxies should die. Old ones, sure. Galaxies that had billions of years to burn through their fuel, collapse inward, and slowly go quiet. That made sense. A galaxy 15 billion years old running low on gas? Expected. Reasonable. Consistent with everything we knew. So when the James Webb Space Telescope started staring into the earliest stretches of the universe, nobody was prepared for what it found. Dead galaxies. Ancient ones. Massive ones. Sitting there in the infant universe like tombstones in a kindergarten. These galaxies had packed 15 billion times the mass of our sun into stars. They had done it fast, and then they had stopped completely before the universe was even 1 billion years old. Scientists call them quiescent galaxies, officially neutral language. But the real word floating around every lab studying them was simpler: dead. And that was the problem. The universe was barely a toddler. Galaxies at that age should have been roaring with activity, drowning in gas, pumping out stars at furious rates, expanding and merging and growing in every direction. The models were clear about this. The simulations agreed. Everyone expected the early universe to look like a construction site. Instead, James Webb kept sending back images of quiet, red, finished galaxies. Galaxies that had grown fast, burned bright, and then gone completely dark. Some of them had stopped forming stars so early that researchers had to check the instruments twice. A galaxy that massive, that quiet, that early, the math said it should not exist yet. Astronomers called this the galaxy quenching problem. Something had to be turning off star formation so completely, so quickly, that these galaxies never recovered. Whatever the killer was, it had to be powerful. It had to be fast. And it had to be leaving behind billions of solar masses of silence as evidence. For years, nobody caught it in the act. The dead galaxies were already cold by the time any telescope looked at them. Reading their light was like finding a campfire with no smoke, no warmth, no embers. Something had been there, something had burned bright, and then something had taken all the fuel away. That is what made the discovery of Crystal 02 so important. Scientists finally found a galaxy at the exact moment the killing was happening, not after, during. A galaxy system 1 billion years after the Big Bang, caught mid-blowout, actively losing the gas it needed to survive. James Webb and a second telescope, called the Atacama Large Millimeter Array, watched the gas streaming away in real time. 7,000 light-years of cold plume, escaping into intergalactic space faster than the galaxy could replace it. The galaxy was alive, but the clock was running. And now scientists had a front-row seat to watch what was always supposed to be invisible. But what was doing the killing? That answer turned out to be more surprising than anyone expected. 13.8 billion years ago, the universe began. Everything that exists, every atom, every star, every galaxy, every black hole burst into existence in a single instant, so hot and dense that our current physics breaks down trying to describe it. For the first 380,000 years, the universe was just a glowing soup of energy, no atoms, No structure, just heat, pressure, and expanding space. Then the soup cooled enough for electrons to snap onto protons. Hydrogen formed. The universe went dark. Astronomers call this the cosmic dark ages. And for about 150 million years, nothing you could point a telescope at existed. Then gravity got to work. Hydrogen drifted. Clumps formed. Those clumps pulled in more gas. The gas compressed and heated, and eventually, ignition. The first stars blazed to life somewhere around 150 to 200 million years after the Big Bang. They were enormous, hundreds of times the mass of our Sunday. So massive, they lived only a few million years before exploding and seeding the universe with heavier elements. In the early universe, conditions were extreme in a very specific way. Gas was everywhere. Gravity was aggressive. Dark matter, the invisible scaffolding that makes up most of the universe's mass, had already started pulling matter into dense webs called the cosmic web. Along those web threads, gas funneled down like water along a spider's silk into the densest nodes, into the centers of what would become galaxies. The first billion years of cosmic time should have been a golden age for galaxy growth. More gas than at any other point in history. Dense, chaotic conditions. Constant collisions between small proto-galaxies merging into bigger ones. The models predicted this era would look like a frenzied construction boom on the largest scale imaginable. And in many ways, they were right. The galaxies that James Webb has seen from this era are packed with young stars, glowing in hot blue and ultraviolet light, forming new suns at rates hundreds of times faster than the Milky Way forms them today. Some early galaxies were building a new star every day. Some were building several. The universe's first billion years were productive on a level that is almost impossible to picture. A billion years sounds like forever, but on cosmic timescales, it is a sprint. These early galaxies had to build themselves from scratch, accrete gas, spark star formation, grow their mass, and establish structure all in what amounts to a blink. Here is what made the problem so sharp. If these early galaxies had access to so much gas, such fertile conditions, such rapid growth, why did so many of them stop? The conditions were perfect for making stars. The fuel supply should have kept flowing. The collisions that were merging galaxies together were pumping in fresh raw material constantly. And yet, massive dead galaxies appeared before the universe was even a billion years old, built fast, burned bright, went dark. Something had taken all that gas away, something powerful enough to strip a galaxy clean, fast enough to do it before the universe grew its second birthday, and violent enough that it left these enormous structures with nothing left to work with. The cosmic boom should have continued. The math said so, but something hit the off switch. What that something turned out to be a wind, a storm born from the galaxy's own fires, is the kind of discovery that makes astronomers stop mid-sentence. And where that wind comes from is stranger still. 1 billion years after the Big Bang, in a dense, chaotic region of the early universe, a group of galaxies is in the final stages of smashing into each other. Scientists call the system Crystal 02. Its light has been traveling toward Earth for 12.7 billion years. By the time it reaches James Webb's mirrors, it carries the story of something extraordinary. A galaxy system caught in the act of dying. Crystal 02 is massive. Its total stellar mass is about 10 billion times the mass of our Sunday. That puts it in the heavyweight category for galaxies at that cosmic age, a serious, grown structure in a young universe. It is sitting in one of those dense cosmic web nodes where gas funnels in and galaxies cluster together, and collisions are almost inevitable. The system is forming stars aggressively, around 260 new suns per year. For comparison, the Milky Way today forms roughly 3 to 5 stars per year. Crystal 02 was forming stars about 50 to 80 times faster than our galaxy does right now. That sounds like a sign of life, and it is. But it is also a sign of something else. The same engine driving all that star formation is also powering its destruction. When astronomers pointed both James Webb and the Atacama Large Millimeter Array at this system, they saw something that stopped the team cold. Extending from the galaxy's disk above and below it, like steam from a pressure cooker, was an enormous plume of gas, cold gas. The kind of gas that galaxies use to make stars, the kind of gas that, once it's gone, cannot easily be replaced. The plume stretched around 7,000 light-years from the center of the system. To picture that, 1 light-year is about 6 trillion miles. 7,000 of those in a column of escaping material. The plume was nearly as long as the galaxy system itself. If you could see the whole structure laid out in front of you, the gas tail would look like smoke pouring from a city on fire. And it was moving fast. The gas in the outflow was clocked at hundreds of miles per second. Scientists estimated the true escape speed of the fastest material at somewhere between 460 and 800 miles per second, after accounting for the angle they were seeing it from. The escape velocity of Crystal 02, the speed something needs to reach to leave the galaxy and never come back, is around 370 miles per second. Some of that gas was already past the point of no return. Here is the number that hit the team hardest. Crystal 02 was losing around 520 solar masses of gas every single year. Its rate of star formation was around 260 solar masses per year. The galaxy was losing gas twice as fast as it was turning gas into stars. Every year, it formed new stars. It shed twice that amount into intergalactic space. Rebecca Davies, the lead scientist on the study from Swinburne University in Melbourne, put it plainly. The galaxy, she said, could be dead in less than 50 million years. 50 million years sounds long, but 50 million years ago, on Earth, the dinosaurs had already been gone for 15 million years. On the scale of cosmic time, 50 million years is basically tomorrow. James Webb and the Atacama Array had not just found a dead galaxy. They had found one dying in real time, with all the evidence still streaming away in a glowing cold plume. The question now was, what started the wind? Two galaxies heading toward each other is nothing like two cars crashing on a highway. Space inside a galaxy is mostly empty. Stars are so far apart from each other that even when two galaxies pass directly through one another, actual star-to-star collisions almost never happen. The distances between stars are just too enormous. If you shrunk our entire solar system to the size of a quarter, the nearest star would still be about 2 miles away. Galaxies full of those quarters running into each other still have room to pass through without the quarters touching. So what actually happens when galaxies collide? Gas. Gas is what matters. Gas clouds in galaxies are enormous. Unlike stars, gas clouds are not tiny points. They spread across hundreds of light years, overlapping and merging when galaxies close in on each other. When two galaxies start to interact, their gas clouds do collide. They slam together, compress, heat up, and in the right conditions, collapse into new stars at a furious rate. The gravitational pull of one galaxy also distorts the shape of the other. Stars get flung into long tidal tails, arms of material stretched outward, like taffy by the gravitational interaction. Gas gets channeled inward toward the center of the merging system. Dark matter halos the invisible scaffolding around each galaxy begin to intermingle and pull at each other. Galaxy collisions happen in stages. First pass, the two galaxies swing through each other, leaving trails of disturbed gas and young stars in their wake. They move apart, then gravity pulls them back. Second pass, closer, more violent, more gas compressed, more star formation triggered. This keeps going sometimes over hundreds of millions of years until the two galaxies spiral into each other and merge into one larger structure. Crystal 02 was in the final stages of this process. Multiple galaxies caught in the closing act of a merger. The gas had already been channeled inward, already been compressed. Star formation had gone into overdrive. The system was burning bright and building fast. But galaxy mergers carry a hidden cost. When gas gets compressed fast enough, the stars that form are enormous. dozens or hundreds of times the mass of our Sunday. And massive stars do not live long. They burn through their fuel in just a few million years. Then they explode. In Crystal 02, the merger had triggered so many massive stars at once that their deaths were happening in waves, explosion after explosion, each one pushing a shock wave through the surrounding gas, each one adding energy to the outflow building above and below the galactic disk. The merger that created Crystal 02's star-forming burst was the same merger that was now killing it. And the weapon it used was something every single star in that system had been building toward from the moment it was born. When Crystal 02's component galaxies began their final approach, something dramatic happened to the gas between them. Normally, gas in a galaxy drifts. It forms clouds, slowly swirls, gradually cools, and collapses into stars over millions of years. The process is steady. It has a pace. Even fast star-forming galaxies in the early universe build their stars over relatively long timescales. A merger changes everything about that pace. As the galaxies closed in on each other, their gravity funneled enormous quantities of gas toward the center of the combined system. Gas that had been spread across thousands of light years was suddenly squeezed into a much smaller region. Pressure climbed. Temperatures in the gas clouds spiked, and when the clouds reached the right density and temperature, they did not slowly drift into star formation, they exploded into it. Scientists call this a starburst. The name fits. A starburst is what happens when star formation stops being a steady drip and turns into a flood. Instead of a handful of new stars forming per year, thousands can form in the same period. The gas clouds, under intense compression from the merger, skip the slow gravitational collapse phase and rush straight into star creation. Entire stellar nurseries light up at once. In Crystal 02, scientists measured the star formation rate at around 260 new solar masses of stars per year. That is starburst territory. The system was building roughly 50 to 80 times more stars annually than the Milky Way builds today. Here is what made this phase so consequential. The conditions that drive a starburst also determine which kinds of stars form. When gas compresses fast and hot, the stars that form tend to be massive. We are not talking about stars like our Sun, which weighs in at a comfortable mid-range mass. We are talking about stars that are 10, 30, 50, or even 100 times more massive than our Sunday. Those massive stars are spectacular to look at. They blaze at temperatures our Sun cannot match. They pump out ultraviolet light and stellar winds that heat the surrounding gas. They light up their nurseries from the inside out, creating glowing clouds that can be seen from across the universe. But they have one fundamental problem. The more massive a star is, the faster it burns through its fuel. Our Sun will last about 10 billion years before it exhausts its hydrogen core. A star 10 times as massive might last only 20 million years. A star 30 times as massive might last only a few million. The biggest stars in a starburst, the true giants, live just 1 to 3 million years before they reach a point of no return. Crystal 02's starburst had created a galaxy full of time bombs. The merger had packed the system with massive, furious, short-lived stars, and as those stars burned through their fuel and began to die, they did not go quietly. They exploded, and the explosions were just getting started. A massive star lives nothing like our Sunday. Our Sun is middle-aged, stable, and predictable. It converts hydrogen into helium in its core at a slow, controlled rate, generating enough energy to hold itself up against its own gravity. It has been doing this for 4.5 billion years. It will keep doing it for roughly another 5 billion. Our Sun is, by stellar standards, boring. And that boringness is exactly what made life on Earth possible. A massive star has no patience for that. Take a star, 50 times the mass of our Sunday. The moment it forms, it faces an enormous gravitational crush. Its own weight is trying to collapse it inward. To resist that, the star has to burn its fuel aggressively, not slowly, but at a rate that would exhaust our Sun in a fraction of its normal lifetime. That kind of star burns so hot that it glows blue-white. It pumps out energy at a rate millions of times greater than our Sunday. It radiates so powerfully that it blows its outer layers away as a fierce stellar wind even before it dies. And it dies fast. A star 50 times more massive than our Sun might live only a few million years. In cosmic time, that is almost nothing. For comparison, the dinosaurs lived on Earth for about 165 million years. A massive starburst star lives for a fraction of that before it hits the end. When it does, the process is sudden and violent. The star's core, which has been fusing hydrogen into helium, then helium into carbon, then carbon into heavier and heavier elements, eventually builds up an iron core. Iron is the end of the line. Stars cannot fuse iron to release energy. Iron fusion actually absorbs energy instead of releasing it. So when that iron core reaches a critical mass, the outward pressure keeping the star alive collapses in an instant. The core falls inward in under a second. The outer layers follow and then violently rebound off the collapsing core. The result is an explosion called a supernova. In those few seconds of rebound, the star releases more energy than our Sun will produce across its entire 10 billion year lifetime. It briefly outshines an entire galaxy. The shock wave from that explosion blasts outward through space at thousands of miles per second. It sweeps up the surrounding gas. It heats everything it touches. In Crystal 02, this was not happening to one star. It was happening to thousands of them, in waves. One explosion triggering the next, each one adding more energy to the outflow, building a wind that grew stronger with every new death. And the more deaths happened, the harder the wind blew. One supernova in isolation is spectacular. A flash of energy, a shock wave expanding outward, a cloud of enriched gas spreading into the surrounding space. Beautiful, violent, locally significant. But one supernova does not kill a galaxy. What happened in Crystal 02 was different in scale. The starburst had created thousands of massive stars in a compressed region. When those stars began to die, they did not die one at a time. They died in clusters, and their deaths fed into each other in a cascade that built something far larger than any single explosion. Picture it this way. Imagine a massive star explodes. Its shock wave pushes outward into the surrounding gas. That gas gets heated and accelerated. Some of it slams into a neighboring cloud, compressing it, triggering another burst of star formation. Those new stars themselves, massive, live briefly and explode in turn. Their shock waves merge with the first. The combined energy pushes farther, harder, faster. This is what astronomers call supernova-driven feedback. And when you stack thousands of supernovae across a starburst region, the feedback does not just push local gas around. It builds into a coherent outflow, a galactic-scale wind. In Crystal 02, the explosions were happening in what scientists identified as the clump, where the outflow appeared to originate. The gas in that region showed signs of being younger and more actively forming stars than the rest of the system. Stars were still being born there, even as their siblings were dying. The starburst had not fully wound down, it was still active, still adding new massive stars to the pile, still feeding more future explosions into the engine. The wind coming off this system was a mix of gas in different states. James Webb detected warm, ionized gas that had been heated by the radiation pouring off the young stars and stripped of some of its electrons. The Atacama Large Millimeter Array detected cold molecular gas, the raw, star-forming material itself, swept up and carried along by the outflow. Both were moving in the same direction. Both were following the same cone shape, rising away from the galactic disk. Scientists estimate the wind was moving at somewhere between 400 and 800 miles per second, depending on how you measure and correct for viewing angle. The escape velocity of the whole system the speed gas needs to reach to permanently leave and never fall back was around 370 miles per second. The fastest gas in the wind was already past that threshold. It was not slowing down, It was not being recaptured by the galaxy's gravity. It was streaming into intergalactic space, carrying away the raw material of future stars, and it was doing so at a rate twice as high as the galaxy's own star-forming output. Every year, Crystal 02 built new stars. The wind tore away twice the equivalent mass in gas. The galaxy was losing the fight against its own engine, and the evidence of that loss was now visible, stretched out in a cold plume 7,000 light-years long, glowing in radio waves, caught forever in the data from 2 telescopes pointed at the dawn of time. Something even bigger was still to come in this story, because this wind had a shape, and that shape revealed exactly how the killing worked. Visualizing a 7,000 light-year gas plume requires abandoning normal scale entirely. 1 light-year is about 6 trillion miles. The distance from Earth to the nearest star outside our solar system is about 4 light-years. The entire diameter of the Milky Way's disk is roughly 100,000 light-years. 7,000 light-years, then, is a significant chunk of a galaxy, not a fringe event, not a local disturbance. A structure that long, extending from a galactic disk, is a major feature of the entire system. And that is exactly what Crystal 02 showed. The plume detected by the Atacama Large Millimeter Array was composed of cold molecular gas. This is the densest, coolest form of gas in the universe, the kind that forms the raw material for stars. It does not glow in visible light. It emits radio waves, which is why a radio telescope in the Atacama Desert in Chile, sitting at an altitude of 16,000 feet, was needed to find it. James Webb cannot see this kind of gas directly, but the Atacama Array can, and what it revealed was a column of escaping material stretching nearly as far as the galaxy system itself. For comparison, imagine a city skyline with a smoke plume rising from it that is almost as tall as the city is wide. That is what Crystal 02 looked like from above, in radio wavelength, the galaxy burning, the smoke pouring out. The plume was not random or scattered. It extended along a specific axis outward from the disk in a coherent direction, following the path of least resistance above and below the dense central star-forming region. The gas in the plume showed increasingly high speeds the farther it got from the galaxy's center. Material closer to the core was still being accelerated. Material at the tip of the plume was already moving at full wind speed. Scientists extracted the spectra from the plume, essentially reading the light and radio signals coming from the gas to understand how fast it was moving and what it was made of. The broad spread of velocities in the signal was a clear indicator that the gas was outflowing rather than simply orbiting or drifting. Outflowing gas shows a characteristic broadening in its spectral lines, a signature that astronomers can identify against the background of a galaxy's normal rotation. The plume contained around 1.5 billion solar masses of material, 1.5 billion times the mass of our Sunday drifting away from a galaxy that only had a finite reservoir of fuel to begin with. Every solar mass in that plume was a solar mass that could no longer form new stars. It was not going to drift back. The fastest of it was already past the escape velocity threshold and sailing into intergalactic space to join the diffuse thin gas that fills the voids between galaxies. The slowest of it might eventually recycle, might fall back in hundreds of millions of years, when the outflow weakens and gravity slowly recaptures what it lost. But by then, depending on what else had happened to the system, the galaxy might already be long dead. What made this observation different from anything seen before was the combination of seeing both the cold gas plume and the warmer ionized gas simultaneously in the same outflow, moving in the same direction. 2 different telescopes, 2 different wavelengths, 2 different types of gas, 1 unified, catastrophic outflow. That combination told scientists the wind was not a local feature. It was a galaxy-scale event, and its geometry, the shape it carved through space, held the key to understanding exactly how it worked. Speed changes everything in physics. And in the case of Crystal 02's outflow, the speed of the escaping gas is the single number that determines whether a galaxy lives or dies. Here is why. Every galaxy has a gravitational grip on its own gas. Material that moves slowly enough stays bound to the system. It follows orbits, circulates, eventually cools, and falls back in to form new stars. This recycling keeps a galaxy alive. Enriched gas goes out, cools, comes back, forms new stars. A healthy circulation. But gas that exceeds the escape velocity breaks free of that cycle entirely. It leaves the galaxy's gravitational well and enters intergalactic space, where it cannot be recaptured. That gas is gone. The elements it carries, carbon, oxygen, silicon elements built inside stars and scattered by supernovae, leave the galaxy permanently. The raw material for future generations of stars exits the system and becomes part of the diffuse cosmic web between galaxies. The escape velocity of Crystal 02 is around 370 miles per second. That is already fast, much faster than anything we launch from Earth, where escape velocity from our own planet is roughly 7 miles per second. Crystal 02's escape velocity reflects the deep gravitational pull of a galaxy with 10 billion solar masses of stars packed into a relatively small volume. Now look at the wind. Scientists measured the broad component of the gas signal, the part of the spectrum that reveals the fastest moving material, and found outflow speeds around 390 miles per second before correcting for the angle they were observing from. When they applied a correction for the likely inclination of the outflow to their line of sight, the real speed jumped to somewhere between 460 and 800 miles per second. That range matters enormously. Even at the low end of the estimate, the wind was already faster than the escape velocity. At the high end, the gas was moving more than twice as fast as what the galaxy's gravity could recapture. This was not just gas being temporarily disturbed. This was gas on a one-way trip. The mass leaving every year, 520 solar masses, is escaping at a rate that doubles the system's star formation output. For every star Crystal 02 builds, 2 equivalent masses of future star-forming material blow into intergalactic space. Scientists tried to calculate how long the galaxy could sustain this before running out. Even under optimistic assumptions, even assuming some fresh gas might flow in from the surrounding cosmic web, the system appeared to have less than 100 million years of fuel at current rates. Some estimates put the timeline at closer to 50 million years before the reservoir runs dry and star formation shuts off completely. At that point, no more stars, no more energy input into the system. The existing stars age, redden, and slowly cool. The galaxy transforms from a blue, active starburst into a passive red structure, growing fainter, decade by decade, as its stars die without replacements. A dead galaxy, added to the growing list that James Webb has been finding scattered across the early universe. And the speed of this wind, measured from 12.5 billion light-years away, might be the closest scientists have ever come to watching a galaxy's death in real time. What comes next in this story is how 2 telescopes made sure none of this was missed. Numbers without context are just numbers. 520 solar masses per year is meaningless until you feel the weight of it. Our sun is a fairly average star. It has been burning for 4.5 billion years. It holds together a solar system of 8 planets, dozens of moons, and countless smaller bodies. Its gravity controls everything within about 2 light-years in every direction. It is, from our perspective, immense. Crystal 02 was losing the equivalent of 520 suns worth of gas every year, every single year, into space, gone. Another way to picture this: imagine the entire mass of our solar system's sun being ejected from the galaxy every 17 hours. Not every year, every 17 hours, the equivalent of 1 solar mass of raw star-forming gas exits Crystal 02's gravitational reach. Day after day, month after month, year after year. That gas does not vanish, it joins the thin, diffuse background gas that fills the space between galaxies. But from the perspective of Crystal 02, it is as gone as if it had simply ceased to exist. The galaxy cannot reach it. cannot use it, cannot turn it into stars. Now, consider the galaxy's total reservoir. Scientists estimated Crystal 02's total molecular gas supply, the cold gas available for star formation, at around 1.5 billion solar masses. That sounds enormous until you run the math. At 520 solar masses exiting per year, and 260 solar masses being converted into stars per year, the system is burning through roughly 780 solar masses of gas annually. Divide 1.5 billion by 780. You get roughly 2 million years before the gas is gone under ideal conditions, with no replenishment from outside. Even with some gas flowing in from the surrounding environment, scientists estimated the timeline for the galaxy to go dead at somewhere between 50 million and 100 million years. For comparison, 50 million years ago, the earliest primates were just evolving on Earth. 100 million years ago, the dinosaurs were still alive. Those timescales feel old and incomprehensible from a human perspective, but in cosmic terms, they are brief. The universe has been around for 13.8 billion years. 50 million years is less than 0.5% of that total age. Crystal 02 had, at best, 0.5% of the universe's current age left to live. Here is the part that researchers found most striking. The outflow rate, 520 solar masses per year, was around 20 times higher than what scientists typically measure in other massive galaxies from the same cosmic era. This was not a gentle exhale. This was a blowout, an extraordinary release of material that should not have been occurring at this rate, at this scale, this early in cosmic history. And yet it was. One galaxy, one wind, one ticking clock. But the next revelation was that this might not be rare at all. Finding a galaxy-killing wind requires seeing two things that do not look alike at all. The first is warm, ionized gas. Gas that has been heated by radiation from young stars until its electrons have been partially stripped away. This gas glows in specific wavelengths of light, particular colors determined by the elements present and the energy states of those elements. Astronomers read these colors as spectral lines, unique fingerprints for each element at each temperature. Warm ionized gas is what James Webb's near-infrared spectrograph is built to detect. The second is cold molecular gas, gas that has cooled down to just a few tens of degrees above absolute zero. Gas that does not glow in visible or infrared light at all. Instead, it emits faint radio waves. These radio waves carry information about the gas's velocity, density, and structure, but you cannot find them with an optical or infrared telescope. You need a radio telescope array pointed at the right frequency with enough sensitivity to pick up signals from 12 billion light-years away. The Atacama Large Millimeter Array is exactly that. It sits in the Atacama Desert in northern Chile, at an elevation of 16,000 feet, so high that most of the atmospheric water vapor that would absorb radio signals has been left below. The array consists of 66 radio telescopes working together, spread across distances up to 10 miles, combining their data to create images with extraordinary detail. When all 66 dishes point at the same patch of sky, they effectively act as a single telescope far larger than any one of them. The cold molecular gas in Crystal 02 was detected through its emission of carbon monoxide and carbon ionized gas signals, specific radio wavelengths that act as tracers for the dense molecular clouds where star formation happens. The plume extended across the sky in the radio data, stretching nearly as far as the galaxy system itself. Meanwhile, James Webb's near-infrared spectrograph was reading the warm ionized gas, particularly hydrogen emission lines and oxygen emission lines across the same region. The spectrograph does not just measure how bright things are, it measures the velocity of the gas as well by looking at how much the spectral lines have shifted. Gas moving toward the telescope appears slightly bluer than expected. Gas moving away appears slightly redder. The shift is small but measurable, with a telescope as precise as James Webb. What the two instruments saw, when combined, was extraordinary. Both the cold gas and the warm gas were moving in the same direction. Both showed the same broad spread of velocities. Both extended along the same axis above and below the galactic disk. Two completely different forms of gas, detected by two completely different instruments using two completely different physical signals, both pointing unmistakably toward a single coherent outflow. That consistency was what convinced the team. A coincidence would have shown the two gas phases moving independently, or in different directions, or at different velocity spreads. Instead, they tracked together perfectly cold and warm gas, radio and infrared, ground-based and space-based observations, all telling the same story about a wind escaping from a dying galaxy. And the shape of that outflow, the specific geometry it carved through space, told scientists even more about how it worked. Before James Webb and the Atacama Array worked in combination on Crystal 02, scientists had seen galactic outflows. Individual studies had detected warm ionized gas escaping from distant galaxies. Others had found cold molecular plumes in nearby starbursts. Some had inferred outflows from indirect evidence, unusual spectral signatures, disturbed gas patterns, unexpected velocities in the data. But direct, simultaneous imaging of both the cold and warm phases of a single outflow in the early universe that had not been done before at this cosmic distance with this level of detail. The difference matters enormously. Seeing only the warm gas gives you part of the story. Warm ionized gas is easy to heat and accelerate. It does not take much energy to drive ionized material off a galaxy's surface. Radiation pressure from young stars can do it on its own. Seeing warm gas escaping does not necessarily mean the cold molecular reservoir, the actual fuel for future stars, is being lost. The warm gas might just be surface material, blown off without affecting the deeper reserves. Seeing only the cold gas gives you the other part but raises its own questions. Cold molecular gas in an unusual location might be recently arrived material or gas disturbed by a tidal interaction with a nearby galaxy, or a feature of the merger itself rather than an outflow. Seeing both simultaneously moving in the same direction at the same velocity spread along the same geometric axis closes that uncertainty. The outflow is carrying away both the warm surface layers and the cold molecular fuel beneath. The wind reaches deep. The wind is multiphase, meaning it affects gas in multiple forms at once, and that is what makes it genuinely capable of shutting down star formation. Cold molecular gas is the direct precursor to stars. When it is gone, stars cannot form. A galaxy can survive losing warm surface gas. It might even recycle some of it. But losing cold molecular gas at the rate Crystal 02 was losing it, through a wind fast enough to exceed escape velocity, represents something the galaxy cannot easily recover from. James Webb's contribution was the spatial resolution and infrared sensitivity to map the warm gas across the galaxy system in fine detail, identifying which clumps were involved, how far the outflow extended, and what the velocity structure looked like across the whole face of the system. The Atacama Array's contribution was catching the cold plume directly, the visible evidence of molecular gas in flight, extending nearly as far as the galaxy itself, glowing in radio waves from 12.7 billion light-years away. Together, they built the first complete multi-phase picture of a galaxy-killing wind in the early universe. That picture revealed a shape that no single telescope could have found alone. The outflow from Crystal 02 was not a sphere. It was not a random scatter of gas moving in all directions. It had a specific shape, and that shape revealed exactly how the wind worked. Scientists described it as a bicone, two cones pointing in opposite directions, joined at their tips at the center of the galaxy's most active star-forming region. Gas was blasting outward above and below the galactic disk, not sideways, not along the plane of the galaxy, but perpendicular to it, like steam escaping from a pressure valve above and below a flat surface. This bicone geometry is familiar from other galaxies closer to us. When you look at nearby starburst galaxies, galaxies with very high rates of star formation, you often see this same hourglass shape in the escaping gas. The geometry emerges because the galactic disk itself is the densest, most resistant structure in the system. Gas cannot easily punch through the disk sideways. It is blocked by too much material. So the wind follows the path of least resistance, straight up and straight down, above and below the disk's plane. The tips of the bicone in Crystal 02 were where the plume extended farthest, where the cold molecular gas had traveled the greatest distance from the galaxy's center before James Webb and the Atacama Array caught it in. The data. The base of the cones, where the wind originated, was centered on one specific star-forming clump within the galaxy system, the one scientists labeled as the most likely source of the outflow. That clump showed signs of being younger and more intensely star-forming than the rest of the system. Its stellar populations were bluer, indicating stars that had formed more recently. Its star formation rate per unit mass was higher. This was the engine driving the entire outflow, a hot, young, explosive cluster of massive stars churning out supernova after supernova, feeding energy into the base of the bicone and sustaining the wind against gravity. The bicone shape also told scientists something about the outflow's efficiency. By measuring how much material was in the cone at different distances from the center, they could estimate how much gas the wind was carrying per unit of energy input from the supernovae. The answer was that the outflow was carrying far more material than expected, around 20 times more than typical for galaxies at that mass and distance. This was not a normal outflow. Crystal 02's wind was in an extreme class, driven by an extreme starburst, expelling material at a rate that placed it among the most powerful star-driven outflows ever observed. And the shape of those two cones, rising above and below the galaxy's disk, carried the weight of an entire galaxy's future inside them. The gas going up that cone was not coming back. Escape velocity is one of the most elegant and brutal concepts in physics. Every object with mass has a gravitational pull. To break free of that pull permanently, to launch something away and have it never return, you need to give it enough speed to overcome gravity's grip. On Earth, that speed is about 7 miles per second. Hit that speed going upward and you leave Earth forever. Fall below it and gravity eventually wins, pulling you back down. Galaxies have their own escape velocities. For a massive galaxy like Crystal 02, with 10 billion solar masses of stars packed into a system still actively merging, the escape velocity from the center is roughly 370 miles per second. That is the speed a piece of gas needs to reach to leave the galaxy permanently, to break the gravitational connection and drift away into intergalactic space. The outflow from Crystal 02 measured at somewhere between 460 and 800 miles per second in its fastest components. At the low end of that estimate, the gas was moving about 25% faster than escape velocity. At the high end, it was moving more than twice as fast. Either way, the fastest material in the plume was already past the point of no return. Here is what that means physically. Gas moving below escape velocity might still escape the galaxy, temporarily pushed by the wind. It rises above the disk, begins to slow as gravity fights the outflow, and eventually stalls. If it stalls below the edge of the galactic halo, gravity gradually pulls it back. This is called a fountain gas, goes up, slows, falls back, cools, and eventually re-enters the disk to form new stars. Fountains are actually a healthy part of galaxy circulation. Gas moving above escape velocity does not form a fountain. It rises, slows slightly, but never stops because gravity cannot win. The gas passes through the galaxy's outer halo, where the dark matter's grip weakens with distance and enters the intergalactic medium. There, it joins the diffuse background gas that exists between galaxies, enriched with metals and elements from the stars whose deaths drove it out. That gas is lost. The galaxy that made it will never use it again. Scientists estimate that a significant fraction of the material in Crystal 02's outflow, particularly the fastest moving molecular gas, detected at the tip of the plume, has crossed the escape threshold. Gone permanently. Not recycled, not returned, just gone. And with every passing year, more of it joins the permanent list. The remaining gas, the slower material that might eventually fall back, could take hundreds of millions of years to return if the outflow weakens in time. But by then, depending on how much fuel is left, the galaxy may already be silent. What this escape threshold tells scientists is that the killing wind is irreversible in the short term. There is no fix available in time to save Crystal 02's current star-forming phase. 50 million years. The deadline scientists gave Crystal 02 before its star formation could shut off entirely. From a human perspective, 50 million years is incomprehensible. It is longer than civilization has existed by a factor of about 10,000. It is longer than recorded human history by a factor of about 50,000. 50 million years ago, the continents of Earth looked different. The mammals evolving at that time would be unrecognizable to us. 50 million years is genuinely ancient on any human scale. But from a cosmic perspective, 50 million years is almost nothing. The universe is 13.8 billion years old. 50 million years is about 0.3% of that total age. Imagine a person who lives to be 100 years old. 0.3% of their life is about 11 days. For Crystal 02, 50 million years is the equivalent of 11 days left to live, measured against a universe-length lifespan. The clock started ticking when the outflow reached its current rate. Every year the wind blows at this strength. The reservoir drops by 780 solar masses, 520, exiting through the wind, 260, converted into new stars. The total remaining cold gas, as measured by the Atacama Array, stood at around 1.5 billion solar masses at the time of observation. Run those numbers forward. At 780 solar masses per year leaving the system, the reservoir runs dry in roughly 2 million years under the most direct calculation. Scientists push that out to 50 to 100 million years by accounting for the likelihood that some gas will fall back, that the outflow rate might fluctuate, and that some fresh gas might continue flowing in from the cosmic web surrounding the system. Even the generous estimate ends in less than 100 million years. And when the gas runs out, the transition from living to dead is not sudden, it is a fade. Star formation slows as the reservoir empties. The galaxy forms fewer and fewer massive blue stars. The blue glow weakens. The existing stars age, massive ones die, medium ones yellow, small ones persist for billions of years as dim red points. The galaxy shifts in color from bright blue-white to orange to red as the youngest populations die out without replacement. Eventually, the galaxy sits there, an enormous collection of old, dim, red stars with no gas left to make new ones. The structure remains, the mass remains, but the life, the light, the energy, the creative chaos of star formation is gone. Crystal 02, if the outflow holds, will join the list of massive quiescent galaxies that puzzled astronomers before James Webb finally gave them an explanation. And that explanation was about to grow much larger, because the mystery of dead early galaxies was not solved by finding one example. It was solved by asking, how common is this? Before James Webb launched, astronomers had a problem they could not explain. Older telescopes, the Hubble Space Telescope, the Spitzer Space Telescope, ground-based observatories had started finding massive quiescent galaxies at distances that put them in the early universe. Galaxies with the mass of hundreds of billions of suns that had stopped making stars when the universe was only 1 to 2 billion years old. They were unexpected. The models said they should not exist yet, but the pre-Webb telescopes could not see deep enough or with enough detail to study these galaxies properly. Confirming that they were truly dead required spectroscopy reading the detailed light signature of a galaxy to confirm the absence of hot young stars, measure the ages of existing stellar populations, and rule out other explanations. The older telescopes struggled with this at extreme distances. Then James Webb launched in December of 2021 and reached its operating position 1 million miles from Earth in January of 2022. Within its first year of science operations, James Webb began sending back observations that shook the field. Not just one or two massive early dead galaxies, dozens of them, confirmed through detailed spectroscopy, sitting in the early universe, fully formed, fully quenched, in numbers that the best models had not predicted. One galaxy stood out as a record breaker. It carried the name Rubies, UDS QG Z7, and its light had been traveling toward us for 13 billion years. James Webb saw it as it existed just 700 million years after the Big Bang, the earliest massive dead galaxy ever confirmed by spectroscopy. It had accumulated 15 billion times the mass of our Sun in stars, then stopped forming stars entirely before the universe celebrated its first billion years. 15 billion solar masses, built and burned out before the cosmos was even a toddler. The problem compounded as more data came in. James Webb's observations showed that massive quiescent galaxies were not rare in the early universe, they were common. More common than any simulation had predicted. Models that had been built over decades of careful work, incorporating everything known about star formation, gas dynamics, and dark matter structure, were consistently underproducing dead early galaxies by enormous margins. Something in the models was missing. Some mechanism was killing galaxies faster and more efficiently than any simulation had accounted for. Scientists had two main suspects. One was the supermassive black holes sitting at the centers of massive galaxies, feeding on gas, radiating enormous energy, and potentially launching winds powerful enough to clear the galaxy. The other was the galaxy's own stars, specifically the supernova explosions of the most massive ones, which could collectively drive winds strong enough to strip the gas reservoir. The black hole theory had the most theoretical support. Simulations almost unanimously preferred it. Without black hole feedback, the models could not produce dead galaxies early enough or in large enough numbers. But simulations are only as good as the physics they include, and no simulation is a perfect copy of the universe. Crystal 02 was about to complicate the picture in a way nobody had fully anticipated. When astronomers built models of the early universe, they had to make assumptions, good assumptions, based on the best physics available, tested against the best observations accessible at the time. Those assumptions said that the early universe should be full of growing galaxies. Galaxies absorbing gas from the cosmic web, converting it into stars, building mass over time. The most massive galaxies should be the oldest, having had the most time to grow. And they should still be growing, still forming stars, still accreting gas, still in the construction phase, because there simply had not been enough time for them to exhaust their resources and go quiet. The first wave of James Webb observations rewrote that picture immediately. The telescope found massive galaxies that were far too structured for their age. Galaxies with organized disks, clear spiral features, settled stellar populations, galaxies that looked middle-aged when the universe was still young. The standard model predicted that early galaxies should look chaotic, irregular, mid-merger, not organized and mature. James Webb kept finding organized and mature. Then came the dead galaxies. Galaxy after galaxy, confirmed through spectroscopy, that had stopped forming stars before models said they should. The discrepancy was not small. Some of these galaxies had built and quenched so quickly that they should not have existed by any prediction the models could generate. Scientists call this tension between observation and theory a crisis not in the panicked human sense, but in the scientific sense. It means the model is wrong, or incomplete, or missing something fundamental. And when a model built over decades keeps being contradicted by fresh observations, the missing piece tends to be something physical, something the model did not include because nobody knew it needed to be there. The galaxy-killing wind in Crystal 02 offered a candidate for that missing piece. A starburst wind powerful enough to strip a galaxy's gas reservoir in less than 100 million years could produce exactly the kind of rapid quenching James Webb was seeing across the early universe. And Crystal 02 was caught doing it in real time, before the galaxy had gone quiet. A living example of the process that left behind the dead galaxies Webb kept finding. But there was a twist that made the story more complicated. The starburst wind in Crystal 02 appeared to be driven by stars, by supernovae, by the deaths of the very massive stars the merger had created. The simulations, the same ones that struggled to produce enough early dead galaxies, had almost unanimously argued that star-driven winds were not powerful enough to do this job. They said black hole feedback was the primary engine of rapid quenching. Crystal 02 disagreed. A star-driven wind, in a galaxy without a confirmed active black hole, appeared to be blowing a massive galaxy toward death in real time. Either the simulations were wrong about the power of stellar feedback, or Crystal 02 was an exception. And this was the possibility that made researchers most excited, there was something more complicated happening, with both mechanisms working together in different galaxies and different conditions. That debate was still open, and sitting right at its center was another kind of galaxy killer, one powered not by dying stars, but by the most extreme objects in the universe. 2 suspects, 1 dead galaxy, a debate that has been running for decades. When scientists try to explain why massive galaxies stop forming stars so quickly in the early universe, they reach for 2 very different explanations. Both are physically plausible, both have observational support, and both make predictions that can, in principle, be tested. The first is the black hole theory. Every massive galaxy appears to have a supermassive black hole at its center. These black holes can grow by consuming surrounding gas, and while they feed, they release enormous amounts of energy. That energy has to go somewhere. In many cases, it goes into the surrounding gas, heating it, pushing it outward, driving winds off the galaxy's face. This process is called active galactic nucleus feedback, or black hole feedback. Simulations of galaxy formation have relied on this mechanism heavily. Without it, the largest galaxies in the models grow too fast, form too many stars, and end up far more massive than the galaxies astronomers actually observe. Black hole feedback acts as a regulator, a governor that limits how big galaxies can get and how long they stay active. The second is the starburst theory. When massive stars die in supernovae, they release energy. When thousands of them die in rapid succession, driven by a merger-triggered starburst, the combined energy can build a coherent galactic wind. Stars are not as energetically extreme as active supermassive black holes. Individually, their contribution is modest, but collectively, in a starburst phase, they can drive powerful outflows that strip gas from a galaxy's reservoir. The problem with the starburst theory, in the eyes of most simulators, was one of timing and power. Stellar winds are short-lived. They depend on having massive stars alive and dying. Once the starburst ends and the massive stars are gone, the wind weakens. A black hole, by contrast, can sustain its feedback for much longer, fueled by a persistent gas supply falling continuously inward. Simulations consistently found that stellar feedback alone was not enough to permanently quench the most massive early galaxies. Black hole feedback was needed to finish the job. Crystal 02 arrived as a complication neither camp was fully prepared for. The outflow appeared to be stellar in origin, driven by supernovae from the starburst, with no confirmed active black hole powering the wind. And yet the outflow was powerful enough that, if it continued, it would quench the galaxy before it had a chance to recover. Either the simulations were underestimating what stellar feedback could do, or Crystal 02 was catching a blowout phase that would eventually give way to black hole feedback as the next stage. Or the real answer was that different galaxies die by different means. That last option opened a door that nobody had seriously modeled before. And sitting just behind that door was a very different kind of galaxy killer, one that made stellar winds look almost gentle by comparison. The simulations were almost unanimous. To kill a massive galaxy fast, in the early universe, you need a supermassive black hole doing the heavy work. The reasoning made sense. Supermassive black holes can sustain feedback for millions or even billions of years, continuously heating and expelling gas as long as new material falls into them. Stars, by contrast, are temporary. A starburst lasts a few tens of millions of years at most before the massive stars all die and the wind weakens. After that, the galaxy might recover gas cools, falls back in, and star formation resumes. So when scientists analyzed Crystal 02 and found no strong evidence of an active supermassive black hole driving the outflow, the result landed awkwardly. The spectral signatures James Webb collected from the galaxy system did not show the high-energy emission lines that would typically indicate a powerful active nucleus. The outflow velocities, while extreme, were consistent with what stellar feedback can produce in the most intense starburst environments, not the extreme relativistic winds that a feeding supermassive black hole can generate. The geometry of the bicone outflow matched what star-driven winds look like in nearby starburst galaxies, scaled up to the much greater star formation rates of Crystal 02. The evidence, taken together, pointed toward stars as the primary engine. Supernovae, thousands of them, stacked in sequence, each adding its shockwave to the growing wind, each depositing more energy into the outflow until the combined force of stellar death was blowing a galaxy apart from the inside. This was the part that the team found both exciting and unsettling. Exciting because it opened a new pathway for galaxy death that theorists had underestimated. If a pure starburst, no black hole required, could generate outflows powerful enough to strip a galaxy of its gas in less than 100 million years, then the models needed updating. The death toll of early galaxies killed by their own star formation might be higher than anyone had calculated. Unsettling because the process was so self-defeating. The galaxy's most productive phase, its greatest burst of star creation, driven by the collision that brought galaxies together, was simultaneously building the weapon that would end it. Every massive star the galaxy made in its starburst phase became a future supernova. Every supernova added energy to the wind. The more productive the starburst, the faster it drove itself toward extinction. A galaxy building stars as fast as it could, each new star a countdown timer, each explosion a contribution to the wind that would eventually blow the whole system quiet. And yet, the debate was still open, because in other parts of the early universe, black holes were doing something similar and doing it on an even more extreme scale. Not all galaxy-killing winds are born from stars. Some come from something older, denser, and far more energetic. They come from the supermassive black holes sitting at the centers of the most luminous objects in the known universe. A supermassive black hole in an active feeding phase is surrounded by a structure called an accretion disk. Gas and dust spiral inward toward the black hole, forming a flat, rotating disk of material that heats up as it falls inward. The friction and compression inside the disk drives temperatures to extreme levels, far hotter than any star's surface. The disk radiates this energy outward as light across the full spectrum, from radio waves to ultraviolet to X-rays. When a black hole feeds aggressively enough, the disk becomes so bright that it outshines every star in the entire galaxy surrounding it all, hundreds of billions of them combined. This is what astronomers call a quasar. The name came from the early days of radio astronomy, when these objects were discovered and briefly thought to be stars' quasi-stellar radio sources, shortened to quasars. The radiation pouring off a quasar does something important. It pushes. Light carries momentum. When an enormous quantity of light, the full power output of a quasar, hits surrounding gas, it exerts pressure. That pressure can accelerate the gas outward. In some cases, the acceleration is modest. In other cases, when the quasar is luminous enough and the gas density is right, the radiation pressure can drive a wind off the accretion disk itself that reaches velocities approaching 1/10 of the speed of light. That disk wind then sweeps through the galaxy. It shocks the surrounding gas. It transfers its momentum outward. And what started as a wind near the black hole can grow into a galaxy-scale outflow carrying far more energy than the original disk wind alone, because the swept-up gas and the shock heating amplify the original push. This is quasar feedback. And when it operates at full power, it does not just halt star formation. It can blast the galaxy's gas supply clear into the intergalactic medium, leaving behind a structure so thoroughly depleted that star formation stays shut off for billions of years. Crystal 02 appeared to be killed by stars. But in other galaxies, some of them even older, the black hole was doing the killing directly. And one of those cases had already been caught, 700 million years after the Big Bang. That is how far back astronomers had to look to find the earliest confirmed galaxy-scale quasar wind. The object carrying the designation J1000 and 7 plus 2000, 115, sits so far away that its light has been traveling toward us for 13.1 billion years. By the time James Webb studied it, this quasar had already been identified as one of the 3 earliest quasars ever observed. But what James Webb found when it examined the system closely made it stand out from all the others. A wind, a galaxy-scale wind, blasting outward from the quasar's host galaxy at a speed that made the numbers difficult to process at first. 4.7 million miles per hour. That is the measured velocity of the material in J, 1007 plus 2000, 115's quasar wind. 4.7 million miles per hour, around 4,000 times faster than the fastest spacecraft humanity has ever launched. At that speed, you could travel from Earth to the Moon in about 5 seconds. The wind stretched outward from the central black hole for 7,500 light-years, comparable to the plume seen in Crystal 02, but driven by a completely different mechanism. Instead of thousands of supernovae feeding a galactic-scale outflow, this wind was launched directly from the accretion disk around the supermassive black hole, powered by the radiation pressure of a quasar so luminous it could be seen from across most of the observable universe. This was the earliest known case of a supermassive black hole actively reshaping its host galaxy through a wind powerful enough to affect the entire galaxy's structure. What made it significant for the broader picture of galaxy death was the timeline. 700 million years after the Big Bang, even earlier than Crystal 02, which existed at around 1 billion years. The black hole driving this wind was feeding aggressively, pouring energy into its surrounding gas, blasting material outward before the universe had barely begun. Scientists confirmed the finding through James Webb's near-infrared spectroscopy, reading the velocity signatures of ionized oxygen in the outflow. The broad emission lines spread across a wide range of velocities were unmistakable evidence of fast-moving, outflowing gas. The spatial extent of the outflow, confirmed across the face of the galaxy system, put it firmly in the category of a galaxy-scale event, not a local phenomenon near the black hole. J1000 and 7 plus 2000, 115 showed that quasar-driven winds were operating in the very first billion years of the universe. At cosmic timescales, even earlier than where Crystal 02 lived, and the fact that this was the earliest confirmed example suggested many others were waiting to be found. The universe's first billion years were full of galaxy killers, some powered by stars, some powered by black holes, all operating faster and more violently than most models had anticipated. And Crystal 02 pointed to a reason why this might be so widespread. Crystal 02 was not an isolated case of galaxy collision triggering a starburst, triggering a wind. When scientists looked at the broader population of massive galaxies from the same cosmic-era galaxies existing within the first billion to 2 billion years after the Big Bang, they found something striking. Nearly half of them showed signs of interacting with neighbors, companions, merging systems, disturbed morphologies that pointed to ongoing or recent collisions. Nearly half. In the local universe today, galaxy mergers are relatively rare events. Large galaxies like the Milky Way collide with major partners only every few billion years. The universe today is spread out, expanded, with galaxies separated by enormous distances that make close encounters infrequent. Mergers happen, but they are events rather than a constant condition. The early universe was different. Galaxies were clustered more tightly, The cosmic web had funneled matter into dense nodes, where many galaxies formed in proximity to each other. The universe itself was smaller not in the sense of having boundaries, but in the sense that the space between objects had not yet expanded as far as it has today. Galaxies that formed in the same dense region of the cosmic web were natural neighbors. They pulled at each other gravitationally. They collided, merged, built larger structures, and triggered new rounds of star formation in each other as they did. In that environment, collisions were not rare events. They were the dominant mode of galaxy growth. And if collisions reliably trigger starbursts, and starbursts reliably drive winds, and winds reliably strip gas reservoirs faster than galaxies can replenish them, then nearly half of all massive early galaxies might have experienced exactly what Crystal 02 was experiencing when James Webb caught it. Rebecca Davies, the lead scientist on the Crystal 02 study, described the early universe's dense regions as cities. Active, chaotic, collision-prone cities where galaxies were constantly interacting, merging, triggering bursts of activity, and then being stripped of their fuel by the same fires those bursts ignited. Dense regions of the universe were like very active cities, she said. Galaxies collide and undergo frenzied bursts of star formation. The biggest stars burn out, explode as supernovae, and launch powerful winds that blast away the very gas galaxies need to keep forming stars. That city analogy captured something important. In a city, the most densely populated areas are also the most energetic, the most chaotic, and in the case of early galaxies, the ones most likely to burn themselves out. The cosmic cities of the early universe were generating their own destruction at an extraordinary rate, and understanding exactly how widespread that destruction was required, looking at what the collisions were actually doing on a structural level. Imagine the early universe as a map of cities. Some regions are open countryside, sparse, spread out, with galaxies growing slowly and relatively undisturbed. Others are dense downtown cores packed with galaxies, gas-rich, constantly churning with activity and interaction. The cosmic web determined which regions became which. Dark matter, the invisible material that makes up most of the universe's mass, had been clumping since the Big Bang, pulled by gravity into a vast three-dimensional web. Along the strands of that web, ordinary matter flowed. Gas collected along the threads and pooled at the nodes where strands crossed. Those nodes became the densest regions in the universe, the cosmic cities. In those cities, galaxies formed early and fast. The abundant gas supply meant star formation ran at extreme rates. The density of nearby neighbors meant collisions were frequent, and those collisions did something specific to the internal gas dynamics of each galaxy they involved. When two galaxies approach each other in a dense cosmic city, their gas does not just compress at the point of contact. The gravitational interaction reshapes both galaxies, simultaneously pulling gas toward the center, stripping material from the outer edges, creating channels through which gas funnels rapidly inward to the densest star-forming regions. The collision reorganizes the gas supply in both galaxies before they even fully merge, funneling enormous quantities of fuel into the very regions where the starburst will ignite. This is why galaxy mergers in dense regions produce such extreme starbursts. The collision is not just adding two galaxies together, it is actively reorganizing the gas in both, directing it toward the center, compressing it past the threshold needed for rapid star formation, and creating ideal conditions for a brief but furious burst of stellar production. Crystal 02 was sitting in exactly this kind of cosmic city environment, a dense node of the early cosmic web where multiple galaxies had clustered together, interacted, and were in the final stages of a multi-body merger. The system was not unique to its region. Other galaxies around it were likely undergoing similar processes, building fast, merging, triggering starbursts, launching winds. Scientists studying the broader survey that found Crystal 02, a program called the Crystal Survey, using both the Atacama Array and James Webb, found 18 galaxies in the same general region of the early universe. Crystal 02 was the standout, caught in the most extreme blowout phase. But it was surrounded by a population that shared many of its characteristics: dense region, multiple interacting galaxies, high star formation rates, potential for collision-driven starbursts. The cosmic city was full of galaxies walking the same path as Crystal 02, and the road that path led to was becoming clear. But the question scientists were now asking was sharper than just why galaxies died. It was about what happened to all the gas they lost and where it ended up. Finding a galactic wind involves reading light that most people would not know how to interpret. The signals are subtle shifts in specific colors, widening of particular spectral features, ratios between emission lines that only make sense if you know what caused them. Scientists call one of these signals shock excitation. It is one of the clearest fingerprints of a galactic outflow. Here is how it works. When gas in a galaxy sits quietly forming stars, orbiting in the disk, behaving itself, it emits light at specific wavelengths. These wavelengths are determined by the elements present and the conditions those elements are in. Hydrogen emits at predictable colors. Oxygen emits at predictable colors. The exact intensity ratios between different emission lines tell scientists what is heating the gas. In a normal galaxy disk, the gas gets most of its energy from ultraviolet radiation emitted by young stars, a process called photoionization. The emission line ratios produced by photoionization have a specific signature that astronomers have characterized in hundreds of thousands of galaxies. But when gas is hit by a shock wave, the physical impact of a fast-moving wind slamming into surrounding material, the energy input is different. Shocks heat gas through compression and collision rather than radiation. The emission line ratios shift. The specific pattern of excited oxygen lines and hydrogen lines changes in a way that cannot be explained by normal star radiation. In Crystal 02, James Webb's spectrograph detected exactly this shifted pattern in the region of the outflow. The emission line ratios in the area of the bicone did not match normal photoionization. They matched shock excitation. The gas in the outflow cone was being hammered by shock waves, the direct physical consequence of a supernova-driven wind ramming into the surrounding medium. The wind was not just flowing, it was actively shocking everything in its path, heating gas through collision, leaving behind a spectral signature as clear as a fingerprint. This shock signature extended across the same spatial region as the cold molecular plume detected by the Atacama Array. The cold gas and the warm gas, the radio signals and the infrared signatures, the plume and the shock pattern, all aligned, all pointing to the same outflow, operating in the same bicone geometry, driven from the same star-forming clump. Each independent line of evidence confirmed the others. This was the discipline of modern astrophysics, at its most precise, using every available tool to triangulate a physical truth from 12.7 billion light-years away. And that physical truth was now carrying a broader implication. The shock excitation signal, the plume geometry, the escape velocity calculations, all of these were tools scientists could now use to look for the same signature in other galaxies, to survey the early universe for other Crystal 02s, to count how many galaxies were at various stages of this same blowout process. The answer was going to be much larger than one. Every galaxy has a budget, a finite supply of cold molecular gas that it can convert into stars. When that budget runs out, star formation stops. Think of cold molecular gas as fuel in a tank. The tank in Crystal 02, at the time James Webb and the Atacama Array observed it, held approximately 1.5 billion solar masses. That sounds enormous. And for the Milky Way today, which holds a relatively modest gas reservoir, 1.5 billion solar masses would represent an extraordinary abundance. But Crystal 02 was burning through that tank from both ends simultaneously. From one end, the starburst was converting gas into stars at roughly 260 solar masses per year. That is normal consumption, the star formation process using up its fuel as intended. New stars form, shine, and eventually return some of their material back to the galaxy. through stellar winds and supernovae over millions of years. From the other end, the galactic wind was stripping gas out of the reservoir at 520 solar masses per year, twice the star formation rate. And unlike the gas being converted into stars, which at least leaves behind stellar mass and eventually returns enriched material through stellar death, the gas in the wind was escaping, not cycling, leaving. Total annual consumption, combining both processes, around 780 solar masses per year. 1.5 billion divided by 780 gives roughly 2 million years of fuel at maximum burn. Scientists pushed that timeline outward by accounting for real-world uncertainties. Maybe some gas flows back from the galactic fountain, the slower material that did not fully escape and will eventually cool and fall back into the disk. Maybe some fresh gas continues flowing in from the surrounding cosmic Webb filaments that feed galaxies in dense regions. Those inputs could extend the timeline significantly, stretching 2 million years to 50 million, or even 100 million under the most generous assumptions. But here is the constraint that held the upper end in check. The gas inflowing from the cosmic web at this stage of the universe was not unlimited. Crystal 02 was already consuming at a rate far above what typical gas accretion could supply. The numbers did not close without the outflow eventually weakening or the gas supply running dry. And once the cold molecular reservoir drops below a certain threshold, star formation does not just slow, it shuts off. Stars need gas clouds of a minimum density to form. Below that density, the gas cannot overcome thermal pressure and gravity to collapse. The galaxy keeps its remaining gas, but cannot turn it into stars. A strange state, technically gas-bearing, but functionally dead. Scientists call this threshold-dependent shutdown. The galaxy does not need to lose every last solar mass of gas to stop forming stars. It just needs to fall below the density required for gravitational collapse. Crystal 02 was draining toward that threshold. And what happened to the gas it was losing where it went after leaving the galaxy turned out to carry its own significance for the universe. 520 solar masses of gas per year, streaming away from Crystal 02 into the space between galaxies. The fastest portion of it, the material exceeding escape velocity, joins the intergalactic medium. This is the diffuse, thin gas that fills the vast spaces between galaxies. It is not empty space, it contains trace amounts of gas, heated to extreme temperatures by the shock waves of past galactic outflows, quasar radiation, and the collapse of cosmic structure. But it is extraordinarily thin, with gas densities billions of times lower than anything in a galaxy. Gas that enters the intergalactic medium from a galactic wind carries something valuable with it. It carries metals, elements heavier than hydrogen and helium, forged inside stars and expelled through the supernovae that drove the wind. Carbon, oxygen, silicon, iron. These elements are the building blocks of rocky planets and life. And by escaping into intergalactic space, they enrich the diffuse gas between galaxies with chemistry that would not otherwise be there. This enrichment is not insignificant. Scientists have measured the intergalactic medium in the modern universe and found it already contains a surprising amount of heavy elements, far more than could have been produced within the galaxies that currently exist. The enrichment came from outflows across cosmic history, galaxies breathing their chemistry into the space around them, seeding the intergalactic medium with elements that may eventually be incorporated into new galaxies billions of years in the future. The slower portion of the outflow, the material that did not fully exceed escape velocity, follows a different path. It rises above the galactic disk, slows as gravity fights the outflow, and eventually stalls somewhere in the galaxy's outer halo. Over hundreds of millions of years, as the wind weakens, gravity slowly pulls this material back. It cools, flows inward along the halo, and eventually reaches the disk again, enriched now with metals from the supernovae that drove it out, ready to be incorporated into the next generation of stars. This recycling process is called a galactic fountain. In healthy galaxies, it is a normal part of the gas cycle. Material goes out, enriches, cools, returns. In Crystal 02's case, the fountain is operating alongside a permanent loss. Some gas returns. More leaves for good. The material permanently lost to the intergalactic medium from Crystal 02 will never form stars in that galaxy again, but it will drift for billions of years through the cosmic web. Some of it may eventually fall into a different galaxy's gravitational well. Some may linger in the intergalactic medium for the rest of the universe's existence, never recaptured. The elements those atoms contain were built inside stars that no longer exist, expelled by explosions that happened 12 billion years ago in a galaxy that was dying while Earth had not yet formed. And those atoms are still out there, still moving. What this ejected gas implied for our own galaxy and our own future was the part of the story nobody wanted to reach too quickly. The Milky Way is alive, actively forming stars, well supplied with gas. By the standards of large galaxies in the modern universe, it is a healthy, mid-aged spiral with billions of years of productive life ahead of it. It is also, according to every current model, on a collision course. The Andromeda Galaxy, our nearest large galactic neighbor, sitting about 2.5 million light-years away, is falling toward us. The two galaxies have been approaching each other for billions of years, drawn together by their mutual gravity. Current calculations put their first close pass at roughly 4 to 5 billion years from now. The full merger, the two galaxies spiraling together into a single structure, will take several 100 million years to complete after that first encounter. That collision will look very different from Crystal 02's. The Milky Way and Andromeda are both older galaxies with more limited gas supplies than the young, gas-rich systems of the early universe. Their starburst, when the merger triggers it, will not be as extreme. The conditions that made early universe mergers so deadly, enormous gas reserves, high densities, a universe packed with material, do not apply to a merger happening in the modern, expanded, gas-depleted universe. Scientists believe the Milky Way-Andromeda merger will produce a burst of star formation, but a moderate one. The merged galaxy, sometimes called Milkomeda, will likely become an elliptical galaxy over time, with its spiral arms disrupted by the collision. But the burst of new star formation will probably not be violent enough to drive a blowout wind comparable to Crystal 02's. The gas supply simply is not there in the same quantities. So, direct parallel? Unlikely. But the broader lesson from Crystal 02 applies to every galaxy, including ours. The processes that kill galaxies, the depletion of gas through star formation and outflows, the gradual aging of stellar populations, the slow transition from blue and active to red and quiet, are universal. They happen on different timescales in different galaxies, but they happen to all of them. The Milky Way is already in a slow version of this process. Its star formation rate has declined over billions of years as its gas supply has gradually depleted. It forms about 3 to 5 stars per year today, a small fraction of what it produced in its peak formation phase billions of years ago. Without a major merger bringing in fresh gas, it will continue to slowly wind down. Crystal 02 showed what galaxy death looks like when it is fast and violent. The Milky Way is on the slow path, same destination, billions of years of delay. But the lesson buried in Crystal 02's data was about something bigger than any single galaxy. It was about the universe itself, and what it reveals about structure on scales that dwarf even entire galaxies. Galaxy death does not happen in a vacuum. When a galaxy loses its gas, whether through a starburst wind, a quasar blast, or the slow exhaustion of its reserves, that event changes the environment around it. The gas expelled by Crystal 02's wind does not disappear. It enters the intergalactic medium, enriching it with metals, heating it with the energy of the outflow shockwaves, and raising the temperature of the surrounding cosmic environment. That heating has consequences for neighboring galaxies. Cold gas falling from the cosmic web into a galaxy requires temperatures low enough to allow gravitational collapse. If the surrounding intergalactic medium is too warm, heated by the shock waves of galactic outflows and quasar radiation from nearby active galaxies, that infalling gas cannot cool efficiently. It flows in from the Webb but stays too warm to collapse into new stars. The galaxy receives gas but cannot use it. This effect compounds. In a dense region like the one Crystal 02 inhabited, multiple galaxies were losing gas simultaneously. Each outflow heated the local intergalactic medium slightly. Each quasar added radiation pressure. Each merger triggered more supernovae. The combined effect of all these energy inputs on the surrounding environment gradually raised the temperature of the intergalactic gas in that region, making it harder for any galaxy in the neighborhood to accrete fresh, cool gas from the cosmic web. Scientists call this environmental quenching, the process by which the death of galaxies in a dense region makes it harder for neighboring galaxies to stay alive. The cosmic city burns its own infrastructure. The galaxy deaths trigger conditions that accelerate further galaxy deaths. This may explain something puzzling that observers have noticed in the modern universe. The densest clusters of galaxies, regions where hundreds of large galaxies cluster together, are dominated by old, red, dead galaxies. The star-forming spirals and active starburst systems that fill less dense environments are largely absent from the richest clusters. The cosmic city analogy breaks down at this point. The densest cosmic cities are full of empty buildings. The explanation emerging from data like Crystal 02's is that those cities burned themselves out in the early universe. Rapid mergers, extreme starbursts, powerful winds, heated intergalactic environments, all working together to quench the galaxies in the densest regions first and fastest, leaving behind clusters dominated by the aging remnants of galaxies that lived and died before the universe turned 2 billion years old. Crystal 02 was not just showing scientists how one galaxy dies. It was showing them how an entire region of the universe transitions from alive to dead, and the scale of that transition was even larger than individual galaxy clusters. There is a pattern running through the history of the early universe, and it shows up everywhere James Webb points. The most massive galaxies formed earliest. The most massive galaxies quenched earliest. The most massive galaxies that are dead today were already dead before the universe was 2 billion years old. This is the live, fast, die young pattern of cosmic evolution, and it runs counter to everything intuition might suggest. You might expect the biggest galaxies to be the most durable, too large to be disrupted, too massive to be fully stripped, too dominant to lose their gas supplies quickly. In the modern universe, big galaxies often are the most stable. The Milky Way, with hundreds of billions of stars, will keep forming new ones for billions more years. Its enormous gravitational grip holds its gas supply in place. But in the early universe, mass worked against survival rather than for it. Massive galaxies formed in the densest regions of the cosmic web, the cosmic cities. Density meant more neighbors. More neighbors meant more collisions. More collisions meant more mergers. More mergers meant more starbursts. More starbursts meant more supernovae. More supernovae meant more winds. The most massive early galaxies had the most gas to begin with, and therefore the most spectacular starbursts when they collided. Their starburst phases were extreme versions of what less massive galaxies experienced. The winds they generated were proportionally more powerful. The gas they lost was a larger fraction of their total supply because the starburst consumed and expelled it so aggressively. Meanwhile, the gravitational depth of a massive galaxy actually made matters worse in one specific way. Deep gravitational wells draw in more gas from the cosmic web, which is good for star formation. But they also channel that infalling gas more efficiently into the central regions, feeding the starburst more intensely, which powers a more extreme wind. The mass that should have protected these galaxies instead fed the engine of their destruction. And there is another factor. Massive galaxies in the early universe were also more likely to host massive, supermassive black holes. As those black holes grew fed by the same gas the starburst was using, they eventually turned on. And when a supermassive black hole in an active feeding phase switches from quiet consumption to active feedback, it adds its own wind to the starburst wind already operating. Stars and black holes working together, both mechanisms firing simultaneously, both stripping the gas supply from the same galaxy. The most massive galaxies, with both the most active star formation and the most energetic black holes, faced both killers at once. Living fast and dying young was not a choice these galaxies made. It was the inevitable outcome of being born massive, in a dense region, in a young universe with nowhere near enough time to survive what their own size demanded of them. Science does not fail when it gets something wrong. Science fails when it refuses to update after getting something wrong. The models of galaxy evolution built over the past several decades were not careless. They were built with the best available observations, the most sophisticated physics, and computing power that grew steadily over decades to allow increasingly detailed simulations of cosmic structure formation. They made real predictions. Many of those predictions proved correct. The large-scale structure of the universe, the cosmic web itself, the distribution of galaxy clusters, the ratio of different galaxy types in different environments, matched simulated expectations remarkably well. Where the models consistently fell short was in the details of galaxy quenching, specifically in the early universe. The models underproduced massive dead galaxies. When simulations ran forward from the Big Bang to the present, the populations of early quiescent galaxies they generated were smaller, later, and less massive than what astronomers actually found. The discrepancy was not minor. In some cases, models predicted roughly 10 times fewer massive dead galaxies in the early universe than James Webb observed. Several specific mechanisms were underestimated or absent in the models. Stellar feedback, the contribution of supernovae to galactic winds, was frequently parameterized too conservatively. The models included stellar winds, but at levels that reflected smaller, less extreme starbursts than what Crystal 02 demonstrated. An outflow rate 20 times higher than typical for galaxies at that mass was not something the models routinely produced. Crystal 02 showed it could happen, and happen in a galaxy with no confirmed active black hole providing additional feedback. The coupling between merger-driven starbursts and outflow efficiency was also underestimated. The models included mergers, they included starbursts, but the connection between the intensity of the merger, the violence of the starburst, and the efficiency of the resulting wind was not calibrated to match what James Webb and the Atacama Array were actually measuring in the early universe. Environmental effects, the way outflows from multiple galaxies heat the surrounding intergalactic medium and suppress gas accretion. For neighbors were included in some models but not others, and at varying levels of accuracy. The revision demanded by Crystal 02 and similar observations is not a small tweak. It is a fundamental recalibration of how efficiently galaxies can kill themselves, using only the energy of their own star formation before a black hole even enters the picture. Updated models will need to account for starburst-driven winds powerful enough to exceed escape velocity across a significant fraction of the outflowing mass. They will need to handle the multi-phase nature of these winds, cold and warm gas moving together in coherent outflows. And they will need to produce the observed number of early dead galaxies without requiring black hole feedback in every case. That recalibration is already underway, and its consequences reach beyond galaxy evolution into something much larger. One galaxy caught in a blowout phase is a discovery. A pattern of galaxies caught at different stages of the same process is a mechanism. The Crystal Survey, the observational program, that found Crystal 02 studied 18 galaxies from the same cosmic era, using both James Webb and the Atacama Array. Crystal 02 was the most dramatic example of an outflow in the sample, but the broader survey showed that outflows, disturbed gas, and signs of merger-driven activity were common across the population, not exceptions. Nearly half of all massive early galaxies showing signs of interaction with neighbors means the collision-driven starburst wind pathway was not a rare event. If 1 in 10 galaxies that underwent extreme mergers in the early universe experienced a blowout comparable to Crystal 02, the cumulative number of galaxies killed this way across cosmic history could be in the millions. Scale that across the observable universe. The observable universe contains an estimated 2 trillion galaxies in total, A significant fraction of the most massive among them formed and quenched in the first 2 billion years. If even a small percentage went through the crystal 0-2 process merger, starburst, blowout, quenching the number of galaxies killed by their own star formation is staggering. And each of those deaths contributed to the enrichment of the intergalactic medium. Each blowout ejected carbon, oxygen, silicon, and iron into the spaces between galaxies. Each outflow heated the surrounding gas. Each quenched galaxy removed a star-forming engine from its dense cosmic region, reducing the pressure and competition for local gas supplies. The cumulative effect of millions of galaxy deaths on the structure of the universe is not small. The intergalactic medium we see today, enriched with metals, maintained at elevated temperatures, threaded with the chemical signatures of ancient galactic outflows, is partly the fossil record of all the crystal 0-2s that died in the first 2 billion years of cosmic time. What we see when we look at the modern universe is partly the aftermath of an ancient mass extinction, not of life, but of galaxies, whole star-forming systems that burned through their fuel in the early universe and went permanently quiet, leaving behind the clusters of red, dead giants that fill the densest regions of the cosmic web today. And James Webb was finding more examples constantly, building a picture of how systematic and widespread the early galaxy death toll truly was. Crystal 02 was caught at a specific moment, a galaxy mid-blowout, actively losing gas at a measurable rate, with both telescopes pointed at exactly the right region, at exactly the right time. But Crystal 02 is one data point in a survey that is still running. James Webb's mission continues. The Atacama Array keeps taking data, and the questions that Crystal 02 raised are driving a new generation of targeted observations. The most immediate next step is building statistics, finding more galaxy systems at different stages of the same blowout process, some earlier, some later, some caught just as the wind is beginning, some caught just as the gas reservoir is nearly empty, mapping the blowout sequence from first collision to final quenching across a sample large enough to draw reliable conclusions. Scientists are particularly interested in catching galaxies right at the transition point, the moment when star formation drops from starburst levels to a declining fade, and the wind begins to weaken as the massive star population thins out. That transition has never been directly observed. It has only been inferred from the properties of galaxies already deep in quenching. Catching it in real time would close a significant gap in understanding how fast the shutdown actually occurs. Another priority is comparing starburst-driven outflows with quasar-driven ones in galaxies from the same cosmic era. Do galaxies with active supermassive black holes quench faster? Do they produce outflows with different velocities, geometries, or gas phase compositions? Comparing the two populations directly, using the same instruments on systems with and without confirmed active nuclei, will test whether stellar feedback and black hole feedback are truly different pathways to the same end, or whether one reliably dominates. James Webb's upcoming deep field observations will extend the search further back in time, looking for outflows in galaxies that existed even earlier than Crystal 02, closer to the first 500 million years after the Big Bang. If the blowout process was already operating that early, the quenching timeline becomes even more compressed than current estimates suggest. There is also the question of what lies just beyond the observable horizon of current instrumentation. James Webb can see the early universe in extraordinary detail, but there are gas phases and outflow structures that even its instruments cannot fully capture. Future instruments, next-generation telescopes, still in development, will extend the multi-phase mapping of galactic outflows to even greater distances and finer spatial resolution. The field is moving fast. Each new observation of an early galaxy caught mid-quench adds another data point to a picture that is rapidly becoming one of the clearest stories in modern astrophysics. A story about how galaxies live, how they die, and what they leave behind. And what that story means for the universe you are living inside right now is the part that matters most. The universe has been killing galaxies since it was less than a billion years old. Crystal 02 is 12.7 billion light-years away. The light James Webb collected to study its dying wind left that galaxy before Earth existed, before the Sun existed, before the solar nebula that would eventually form our solar system had even begun to collapse. The explosion of every massive star that fed that wind happened in a universe that would not produce our planet for another 8 billion years. And yet the lesson it carries is immediate. Galaxies are not permanent. Star formation is not an indefinite process. The conditions that allow a galaxy to build stars, a supply of cold gas, a gravitational environment that can hold that gas in place, a lack of catastrophic disruption, are temporary. They can be ended by the galaxy's own most violent processes, by the deaths of the very stars the galaxy created. The Milky Way will not die the way Crystal 02 is dying. The timescales are different, the gas supply is different, the merger history is different. Our galaxy is on the slow path, a gradual wind down over billions of years, rather than a catastrophic blowout in under 100 million. But the direction is the same. Every star the Milky Way forms brings it slightly closer to the day its gas runs out. Every supernova enriches the surrounding gas, but also returns some energy to the interstellar medium, slowly warming it, slowly making new star formation slightly harder. Crystal 02 represents the extreme end of a process running everywhere. What James Webb revealed in catching this wind was not just the mechanism of one galaxy's death. It was a demonstration that the universe has built-in limits on how long any given galaxy can stay alive. Those limits are set by physics, by the energy released in stellar death, by the escape velocities of galactic gravitational wells, by the finite supply of cold gas available in any region of the cosmic web. Understanding those limits changes how we understand the universe's future. Galaxies across the cosmos are at different points in their life cycles. Some are just beginning young, gas-rich, forming stars at furious rates. Some are in midlife, like the Milky Way. Some are already dead, their ancient stellar populations cooling in silence, their gas long since blown away by winds like the one Crystal 02 is driving right now. Eventually, far into the future, across timescales that make the current age of the universe look like an afternoon, the universe will run low on star-forming galaxies. Not because the space between them expands too far, though it does, not because dark matter stops structuring, though it will, but partly because the galaxies themselves consumed and expelled their own fuel, because the stars they built exploded and pushed the next generation's raw material beyond reach. Crystal 02, dying 12.7 billion light-years away, is the universe showing us one moment in that long, slow process. A galaxy catching fire, burning bright, and using the heat of its own light to blow itself dark. The wind that killed it was made of the same elements that make up you. Carbon expelled from dying stars. Oxygen blasted into intergalactic space by ancient supernovae. Atoms that wandered for billions of years through the cosmic web before gravity gathered them into new clouds, new stars, new systems, new planets. Everything in the universe is borrowed. Everything in the universe returns. And somewhere, 12.7 billion light-years away, a galaxy is losing its loan, sending it back into the dark, one solar mass at a time.